So segment 2 of chapter 7. In the first segment, we looked at a lot of the definitions for the different solutions, solvent, solute, concentration, solubility, these types of things. And we started to get to the math, and that's where we took a break. So in this segment, we're going to start right off with math, and we're going to be looking at percent solutions. So percent solutions, percent simply means per 100. So the math here is going to be pretty straightforward. What we're going to do is we're going to take the volume of the solute divided by the volume of solution. Looks like this got moved over a little bit here, so this needs to be over here a bit. It should be right underneath, times 100%. Now, because we're doing volume of solute over volume of solution, we're going to indicate that with percent V over V. Okay, percent V over V. Questions will look sort of like this. What is the percent solution if 25 milliliters of methanol is diluted to 150 milliliters with water? And so what we're going to do is we're going to figure out which one is our solute and which one is the solution, the solvent. And so the volume of the solute, what is the percent solution if 25 milliliters of methanol, okay, that's going to be our solute. So we're going to take 25 milliliters is diluted to 150 milliliters. That's going to be our final volume. So that's going to be the volume of the solution. So we're going to put that over 150 milliliters. And then we're going to multiply that by 100%. All right, so we'll get out our calculator. We'll take 25 divided by 150 times 100, and we get 17%, 2 sig figs. So we'll get 17. What we're going to do is go percent, excuse me, V over V, okay? Percent V over V. All right. So again, percent meaning per 100. We can also do mass of the solute over volume of solution, and we'll multiply that by 100%. So it's the same formula, except now the ending, that unit, is going to be percent M over V. Now this is the most common, especially going into the medical profession. This is what you're going to see most of the time, percent M over V. So the first thing, if you go to the hospital, usually what they'll say is you're dehydrated, and they'll want to hook you up with an IV and put in saline solution. And of course, that's going to be M over V. Now, why is it more common? Well, because sodium is a solid, and it's going to be easier to measure out a solid by mass and then put it in a set amount of volume. So that's why it's going to be more common. 4.8 grams of sodium chloride are dissolved in 82 milliliters of solution. What is the percent of the solution? So again, we're going to do it the same way. We're going to take 4.8 grams. We're going to divide that by 82 milliliters. And then we're going to multiply it by 100%. Now here we're just going to ignore that grams, and we're going to ignore that milliliter. So we're just going to recognize that whenever it's percent M over V, it should be grams per milliliter. Divided by 82 times 100. Again, 2 sig figs, so it's going to be 5.9% M over V. Right? Now, second way we can do these equations is how many grams. So sometimes we have to work backwards, figure out how many grams of salt are in 52 milliliters of a 6.3% solution. So now we're going to just do that backwards. So I'm going to take the 6.3%, right, and this should have been M over V. And now instead of multiplying by 100, I'm going to divide that by 100. That's going to get rid of the percent. That's going to give me a decimal format. And then I can multiply by the volume, and that'll give us our mass. So I'm going to take 6.3, divide by 100, then times the 52 milliliters, and that's going to tell me it's 3 3.3 grams. Right, 3.3 grams. All right, now there's also going to be mass over mass percentage. And so the way we would do that is percent M over M. Those are not common at all. So I don't even take the time to put it on a slide. However, you should be prepared for that. If I ask a question that's mass over mass, it's just like these last two, except it'd be grams over grams, and then percent M over M. Now, switching gears back to chemistry, in chemistry, we keep track of concentration with a term called molarity. And of course, molarity has that infamous word in it, mole. And of course, molarity then is the number of moles of solute in 1 liter of solution. So rather than having a mass now, we've got a count, the moles. We represent molarity with a capital M, and so capital M is equal to moles over liter. Right, so it's always moles per liter. Questions here. What is the molarity of a solution with 2 moles of sodium chloride in 4 liters of solution? Okay, so we're going to take 2.0 mole. We're going to divide that by our 4.0 liters, and that's going to give us 0.5 molar. Molar, capital M. What is the molarity of a solution with 3 moles dissolved in 250 milliliters of solution? So here it's going to be very similar. So we're going to take 3 moles, put that on top. But remember, it's per liter, and I've got 250 milliliters. That's going to be 0.25 liters. Right here, the 0 doesn't count, so I didn't put it down here. 2 sig figs. And so that's going to be 12 molar. All right, so that's quick and easy calculations there. Most likely the struggle will be confusing them, but typically you would be good to go at that point. So the next thing we're going to take a look at then is making solutions and how it's going to be a little bit different than what we do in the kitchen. So in the kitchen, we typically just take our liter or quart jar and throw some Kool-Aid in the bottom, throw some water in, mix it up, and life is good. But in chemistry labs, that's not how we do it. So what we're going to do in a chemistry lab, and if I was going to use kitchen materials to perform this the way I would in a chemistry lab, the first thing I'm going to do is I'm going to get my quart jar out and I'm going to put just a little bit of solvent in. So maybe a quarter to a third full. And then what I'm going to do is add the Kool-Aid. Right, I'm going to add the Kool-Aid. I'm going to stir it up, get it dissolved, maybe add heat if I need to warm it up. If it's close and I don't want to warm it up, maybe put just a little bit more water in, maybe the 3/4 mark, get it nice and dissolved. Then I'm going to fill it to the final volume. Right, that's going to give me a much more accurate volume to mole relationship, and that's what we're after. So remember, molarity times the liters would then give me moles. And of course, I can do my reactions in moles, and that's why I would care about that. So I want to be able to calculate pretty accurately the moles and the volume. Now, questions on an exam, what would they look like? Well, how many moles of sodium chloride are needed to make 6 liters of a 0.75 molar NaCl solution? So again, we can follow this formula right here. We have molarity, 0.75 molar, times the number of moles, right? Or excuse me, times the volume would equal the number of moles. So times 6.0 liters. Now remember, this is going to work because big M is equal to moles over liters. And so there my liters will cancel out and I'll be left with moles. Okay? So that's going to be 4.5 moles. All right? Just throw that to my calculator just to make sure. 0.75 times 6. Yep, 4.5 moles. All right. Now, typically we don't go around measuring moles though, right? We measure mass. So, how many grams of calcium chloride are needed to make 625 milliliters of a 2.0 molar solution? So again, we have our big M as moles per liter. We can use that to calculate our moles. And then from chapter, was it 6, I think it was, you can go from liters, oh my gosh, not liters, from moles to mass to grams. All right, so it's going to be a couple steps here. So we're going to start with 2.0 molar, which is going to be the same thing as moles per liter. We're going to times that, but this is in milliliters, so I'm going to divide that by 1,000, right? So it's going to be 0.625 liters. Liters will cancel out. Right now I'd be in moles, but I'm not looking for moles. I'm looking for grams. So the next step is I'm going to get the molar mass for calcium chloride. So calcium is 40.08. 40.08. Chlorine is 35.45. We have two of them plus the 40.08 gives me 110.98 grams over 1 mole. Remember, that came from the periodic table. Okay. Now my moles will cancel out, and I'll be left with grams, which is what I'm looking for. So I'm going to take 2 times 0.625 times 110.98. And how many sig figs are we allowed to have here? Only 2, which means my final answer then will be 140 grams. Okay, my calculator was 138.7. All right. Do some more. 10.3 grams of sodium chloride are dissolved in a small amount of water, then diluted to 250 milliliters. What is the concentration? So 10.3 grams of sodium chloride are dissolved in a small amount of water, then diluted to 250 milliliters. What is the concentration? And we could put comma molarity, right? Now, I want to preface that because you could take 10.3 grams, divide by 250 milliliters times 100%, and you'd have a percent solution of M over V. Okay, but I want molarity. So, to do molarity, we need to take those grams and turn them into moles. So, to get from grams to moles, I'm going to need the periodic table. So I'm going to take sodium, which is 22.99. Double check that. 22.99 plus chlorine, which is 35.43, 35.45. That gives me 58.44 grams per mole. All right. Next, I'm going to take 10.3 grams. I'm going to convert that to moles using that. So for every 1 mole, it's going to be 58.44 grams. That would give me moles, but we want molarity, so we want moles per liter. So grams will cancel out. I don't want moles to cancel out. I want moles to go straight through. So I'm just going to put a 1 there just to hold that. And I want liters to be on the bottom. We're in milliliters, so I'm going to convert that. That's going to be divided by 1,000. So it's going to give me 0.25 liters. All right. Plug and chug time, 10.3 divided by 58.44 times 1 divided by 0.25 gives me 0. And how many sig figs do we get? 3 and then 2. So 70 molar. So 0.70 molar. All right. So if you have questions, make sure you pause, go back, look at it a couple times if you need to, or just get a hold of me. Show up for a student office hour, or if you want, make an appointment, schedule an appointment with me. All right, let's see. Erase all of this mess now. Guess I could have paused the video. I'm so used to doing this in a normal lecture. We'd probably be chit-chatting or you'd be asking questions. All right, how many grams of sugar are needed to make 125 milliliters of a 0.5 molar sugar solution? And I'm going to tell you to go ahead and pause the video and give it a try. And then once you have an answer, then push play and see how you did. All right, so hopefully you've pushed play now. You've got an answer in front of you. How many grams of sugar are needed to make 125 milliliters of a 0.5 molar sugar solution? So I'm going to take 0.50 molar would be moles per liter. I'm going to multiply that by 0.125 liters. Now simply converting these milliliters to liters, I divided by 1,000. And then I'm going to multiply that by, let's see, 1 mole. It should be about 180. So we got 12 times 6 plus 12 plus 96, yeah, 180. I'm going to use 180.16. So we might be a little different there, but it won't matter. It's all going to wash out with the sig figs. But that's the molar mass of that sugar. So I'm going to take 0.5 times 0.125 times 180.16, and I'm going to get to 2 sig figs, 11 grams. So I would need 11 grams of sugar in order to make that solution. All right. The next topic we hit, still along the same vein with the calculations, would be dilutions. So a lot of times when we start out making solutions, it's one of two options. Either we're going to make the solution from a solid, or we're going to have a stock solution that's already in water, and we're just going to add water to it and dilute it down, right? So for dilution, then we're simply adding the water to our solution in order to change the molarity and make it a lower concentration. I do this a lot for our Chem 110 labs, right? So you need to use 1 molar HCl or 1 molar this or 1 molar that. Typically what we'll do is we either purchase or we'll make a stock solution that's like 5 or 10 molar and then dilute down from that to make larger quantities. So in a dilution, what's happening is the number of moles of solute are not changing. But what we're doing is we're adding solvent. So the moles of solute before will equal the same moles after, but the volumes are changing. And by changing the volumes, we're going to be changing the concentration. So the formula then is M1V1 is equal to M2V2, where M1 and V1 are going to be your starting concentration and volume, and M2, V2 are your final concentration and volume. Now the beautiful part is this does not have to be molarity. This will work for your percent concentration solutions as well. So if I'm at 5% solution and I want to be at 3% solution, we could do the calculation to figure out how much water to add. But so it doesn't have to, it's any concentration. It doesn't have to be molarity, even though we're using the symbol for molarity there. Now again, your stock solutions are typically going to be made to a pre-made known molarity, and we would just figure out how much we want to add to it to dilute it down. So 2 liters of a 0.88 molar solution are diluted to 3.8 liters. What is the new molarity? Okay, so again, M1V1 is equal to M2V2. Just like in gas laws, it doesn't matter which ones we set to 1 and 2. We just have to make sure we have the 1s together and we have the 2s together. So 2 liters of a 0.8, these two have to go together. Whether we make them 1 or 2, doesn't matter, but they just have to make sure they're together. So we're going to take 2.0 liters times 0.88 molar, and that's going to equal 3.8 liters times that new molarity, right? So the new molarity then is going to equal 2.0 times 0.88 divided by 3.8. So we get 0.46, and then 3.1. We only get 2 sig figs here. So the nice part about this is, much like gas laws, we can see if that makes sense. So we had 2 liters, we turned it into 4 liters. Did our concentration go up or down? We would expect it to go down, and according to the calculation, it did go down. So we must have done that one correctly. Yay. All right. So let's see. Let's erase that. Used to have erase slide, but I don't see that anymore. So we'll just get rid of that part. I'll leave the formula up there. For our next question, you have 150 milliliters of 6 molar HCl. What volume of 1.3 molar HCl can you make? All right, so this time we're going to set up the same equation. The beautiful part here is, since it says what volume of this can you make and it doesn't give us a unit, we can actually do this in milliliters and not convert to milliliters. So I can take 150 milliliters and multiply that by the 6.0 molar, and that's going to equal 1.3 molar times that new volume. So our new volume then is going to equal 150 times 6 divided by 1.3. And we get 2 sig figs, so this is going to be 690 milliliters, right? So 690 milliliters. Now, if it did ask for liters, then you could have converted the 150 and then did the math there, or we could have gotten in milliliters and now just convert our 690 now. Either way would have worked. All right. Got one more problem, and then we'll call it a segment. All right. So for our last problem, you need 450 milliliters of 0.15 molar NaOH. All you have available is a 2 molar stock solution of NaOH. How do you make the required solution? Now it's asking you how you actually make the solution. So what you're going to do is you're going to say, we're going to add a little bit of solvent, and then we're going to need to add a known amount here, right? So that's the part we have to do some math for. We'll do some math to get that piece. We're going to add this many milliliters of the stock solution, and then we'll fill to the final volume. So we need 450 milliliters of a 0.15 molar NaOH solution. All we have available is a 2.0. So we're going to take 450 milliliters. And we want it to be 0.15 molar. All we have, equals, all we have is a 2.0 molar solution, and we want to know what volume of that would we need. All right, so our volume then would be 450 times 0.15 divided by 2, and we're going to need 34 milliliters. And again, to answer this question, we actually have to have a couple statements here. So, because this is how do you make the required solution? So what we would say is that we would take, let's see, we need 450. So we're going to take 150 milliliters of water. We're going to put that into a volumetric flask. Then we're going to add 34 milliliters of the 2.0 molar stock solution. And then we're going to fill to a final volume with solvent of 450 milliliters. Right? So that one's going to take a little extra work there because it's making sure we know how to make a solution as well as being able to do the calculation. Right? So hopefully that didn't get past you. You saw that coming. If not, it makes sense now that I've put it out there. And so hopefully you're putting this all together and it's making some sense. All right, so for my Chem 110 folks, you have one more segment where we're going to then put all of this stuff back into reactions. Okay, so we'll be coming back at stoichiometry. Now, for the 100 folks, you also have only one more segment, but your segment is going to be segment 4. Right, so you're going to skip segment 3. So segment 3 is going to be all about stoichiometry, and then everybody will have to do segment 4, which will be colligative properties. All right, so stay tuned, and we'll come back to this. So that's it for segment 2.